Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're going to move into what I'm calling Chapter 7 of this playlist, Classification. Now, classification has a simple definition. It's an observation whose group membership is unknown, is assigned to a group based on a vector y of p variables. That's what classification is. It takes a new observation and puts it in a group. Now, first we're going to look at Fisher's linear classification rule. So let's assume we have n observations with p variables per observation that have previously been classified into two groups, G1 and G2. And we wish to classify one observation y with p variables, an unknown assigned group, into one of two known groups, G1 and G2. And so this is Fisher's linear classification process. And in a second, I'll tell you why it's linear. Assume we have a common unknown, so there should be an n there, covariance matrix, sigma. Normality assumptions not required, so this is sort of, well, it's not sort of, it's exactly a non-parametric procedure. Let's compute the mean vector for group 1, the mean vector for group 2, and we need to calculate the pooled estimate of the common variance, right? We're assuming that both covariance matrices are the same. This is the formula for the pooled estimate. And we use the discriminant function, a prime, and see the previous video where this was the discriminant function that best separated the two groups. And then we compute the average for group 1 and the average vector, the average for group 2 through this transformation. So we take the mean vector for group 1 and run it through this discriminant function. We have a value, and then we take the mean vector for group 2 and run it through this discriminant function, and then we have a value for x2. And then we apply the discriminant function to the next or new observation y. Okay, so this y is our new observation that we want to assign to a group. And actually, if you look at this transformation here, so A transpose y, A is a vector. When you take a vector times the vector y, it's a linear combination of those variables. And that's why it's called linear classification, because we're taking a linear transformation of our data to classify. So then we get a value. We get some z value after this. We take our y through the discriminant function. And then it's a simple process. We assign y to G1 if z is closer to the mean for that group, Z1, or we assign it to G2 if z, this transform variable, is closer to Z2 bar, the mean for group 2. And it's as simple as that. And so let's do an example. We have data from an FTP site, which is given here, and we're going to use the data called T51 psych data. There are 4 psychological tests given to 32 men and 32 women. It was from Beale in 1945. The 4 variables are here: Y1, Y2, Y3, and Y4. And the data will partially listed in our illustration below. And suppose that we want to evaluate Fisher's linear classification rule. So let's make this bigger. So we read in the data. Oh, first we have to load the library mask, because that's where the LDA, the linear discriminant analysis function, is. And mask comes with all base installations of R. There's not a header file, so we assign variable names to the columns of y, and here are the data. Here's the first 6 observations. Now we want to calculate the mean vectors for group 1 and group 2, and this is one approach where we create an indicator function, and where I say where min, and we look at the first column and compare it to 1, because then it's a man, and if it's not, it's a woman. And then it creates this vector of trues and false. So when we calculate the mean vector for group 1, we do it like this, and this is for women. So we have Y1 bar, Y2 bar. Now we run the linear discriminant analysis, the LDA function of our data. So it's gender by these 4 variables, and we store it in fit. And we print fit. It generates the group means, and this is the vector A, the linear discriminant function. Okay. Now let's see how our own data does against itself. So if we predict, so we use the predict function. Fit is the model that we generated up here. So we're going to use this rule or this linear discriminant function against the variables in our own data set to see if it predicts them correctly. So we put the estimates in Y. So it takes every Y value, runs it through this linear discriminant, and then puts it in Z. Now, if you're just using your own data to see how it did in the fit, you don't actually need to put it back in the data because that data is already stored in fit. And let's do a histogram of the 2 variables. Oh, let me make it smaller. And this is it. So group 1, after the transformation, it's these values, and group 2 have these values. So notice there's a little overlap here in these histograms. So to use Fisher's linear discriminant function, we calculate Z1 bar. So we put in Y1 bar, and the predict requires a data frame, so we force it to be a data frame, and then we only want the predicted value, or the linear transformation, which is what X is. So Z1 is this. So this is the mean value after transformation for group 1. And the mean value after transformation for group 2 is this. Now, the way LDA works is it forces that transformation such that the average of these 2 values is 0. So if we take Z1 plus Z2 divided by 2, then it's 0. And this is the value that we compare against. If our observation after transformation is greater than 0, it goes to one of the groups, and you can look in here that it'll go to group 2, right? Group 2 is this. It has a bigger mean, or you could see it this way, right? If it's negative, it'll go to group 1. So let's look at the first and fourth observations of our data vector or data matrix or data frame. So first observation is this, the fourth observation is this, and they're both male. And let's see what the Fisher's linear classification rule would have classified them. So we predict, and we're using the fit, so that model, and we want the first and fourth observations, right? Why? This is a data matrix. So the first, before the comma says rows, after columns, we want all the columns. And look what it does. It classified the first observation as group 1 appropriately, but it classified the second observation as class 2 or group 2. So it misclassified it. Right, and here are the Z values after the transformation. The first one was minus 1.4, second one was 1.5. Let's see how well it does with all the variables of Y. So let's predict, let's run each observation that we already know the men and women, the groups through it, and see what the algorithm predicts. So that's what this does. We want to know the class, where does it predict each value? So we put that in predict Y. And then we do just a simple table of the actual group versus the predicted group. And this is it. So notice that uh, of the men, it misclassifies 4 of them. 28 are correct. Of the women, because we know that they're women, it misclassifies 4 and correctly classifies 28. Now, it's just coincidence that it's the same number. That's not usually the case. Okay, well, it's 10 minutes, so I'm going to end this video. And in the next video, we're going to do classification for K different groups, not just 2. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.